Okay. Well, last week we have discussed the interface conditions. Okay, one moment. So let's continue. Sorry for interruption. Well, in the last week we have finished discussing the interface conditions, or in other words, we know this as boundary conditions of electric field and magnetic field. And last week we discussed the boundary conditions for time varying electric fields and magnetic fields. So as a conclusion, so let me open a new book. As a conclusion, we can summarize our lecture with this table. Here, this table shows us the summary of boundary conditions for electric fields and magnetic fields. Now let's see several examples on how to apply these boundary conditions in real problem. Okay, let's consider this example. Okay, and picture A picture A is for our problem. Okay, let me put here. Now, let's read the problem. A magnetic field exists in material 1. So, if you look to the picture, this is the boundary between material 1 and material 2. On the left, there is material 1. On the right, there is material 2. So, magnetic field exists in material 1, okay, as H1 equals, so H1 equals to X plus Y multiplied by 2 minus Z multiplied by 3 cosine 377 T. Okay. Material 1 has a relative permeability of 100. Okay, it is given 100. The interface between material 1 and free space. Okay, material 2 is free space. Here we can see is on the plane Z equals 0. So this is the boundary between material 1 and 2, and there are no currents on the interface. So no currents on the interface, it means current density Js on the boundary is 0. Okay, now we need to find magnetic field intensity and magnetic flux density in material 2. So we need to calculate H2 and B2. Now, now, how do we proceed in this case? First of all, let's look to our summary of our boundary conditions, and we can see for tangential components. Okay, for tangential components of magnetic fields, we have boundary condition which says H1 tangential minus H2 tangential equals to Js. And for normal components, we have the expression which says mu1 H1 normal equal to mu2 H2 normal. Now, we apply these two equations. First of all, before applying these equations, we write the tangential and normal components of magnetic field intensity. Okay, let me write one more time H1. So
GS 0 گرتیم مزخرف ببینن خاصی بربرس گرتیم و پامیده من.
Yes, only tangential components. You are right. Here you are saying about this, yes? Yes, tangential components of H1 and tangential component of H2 will be equal, yes. But normal components are not equal. First of all, let's write the tangential and normal components for H1. Okay, H1 was equal to, let me see, H1 was equal to x plus y multiplied by 2 minus z multiplied by 3 multiplied by cosine 377t. Okay, and let's look to the picture of our problem now. We can clearly see that, so here is H1, something like this, general H1. We can clearly see that normal component of H1 will be along Z. This or this, it doesn't matter. Component along Z will be normal component of our H1. It means H1 normal will be equal to minus Z minus Z multiplied by 3 multiplied by cosine 377t, and tangential component of H1. Tangential component means that it should be our component should be tangent to the surface of our boundary, and tangential component of H1 is x plus y multiplied by 2 multiplied by cosine 377t. Okay, now let's apply the boundary conditions to our field. From the first equation, we can see that first equation says h1 tangential minus h2 tangential is equal to the Js, surface density of current, but we know that there is no current in the boundary, that's why it is 0. That's why tangential component of the magnetic field intensity in the second material H2T will be equal to H1T. And which is, so H2T equal to, okay, x plus y multiplied by 2 multiplied by cosine 377t. Okay, what about normal components? Well, for normal components, we have equation which says that mu1 multiplied by normal component of the magnetic field in the first material equals to mu2 h2n. From here, we can simply write that h2n is equal to mu1 over mu2 multiplied by h1n. And this equals mu1. So I am already recording. Yes, recording is going on. So mu1 was equal to 100 mu0 divided by mu2 was empty space, which is only just mu0 multiplied a normal component of the magnetic field intensity in the first material was equal to minus z multiplied by 3 multiplied by cosine 377t. And from here we can find that normal component of magnetic field intensity in the second material is equal to minus z multiplied by 300 multiplied by cosine 377t. Okay, now we know the normal components and tangential component of the magnetic field intensity in the second material, and total magnetic field H2, total magnetic field intensity H2 will be equal to just the sum of tangential component plus normal component. Which will be equal to x plus 2y y multiplied by 2 minus z multiplied by 300 multiplied by cosine 377t. Okay, we found H2. What about B2? What about B2? Can you suggest how to calculate B2?
Mu0 multiply H2.
Of course. Perfect.
We found mu0.
So, by the definition, B equals to mu by H, and from here we find that B2 will be equal to mu2 by H2. So H2 in our case x plus y multiplied by 2 minus z multiplied by 300 multiplied mu2 is mu0 multiplied by cosine 377t. Okay, we found B2 also. Now, the next example. Okay. Okay, the configuration of the previous example is given, so configuration of this example is given. Well, electric field intensity in material 1 is E1 equal to kx plus y2 minus z3 cosine 377t volt per meter, where k is a constant. Calculate electric field intensity and electric flux density in material 2. So, calculate electric field intensity in material 2. Well, can you do by yourself?
Yeah.
Oh, no reaction. Okay.
Yeah, teacher.
Try to do by yourself. You have 4 or 5 minutes. I will open the main formulas here. Okay, let me copy these formulas. Okay, here are the general formulas for your use. Well, please try to find electric field intensity in the second material, E2. Now you should apply boundary conditions regarding the electric field. Which equation will you apply? It is up to you. So
I use
let me open the new page. Okay, tell me.
First, I use this form normal components epsilon 1 multiply
You mean
E
this,
1
this
normal
one?
minus this
Okay.
rho s 10
Okay.
0
Epsilon. One moment. Sorry. Epsilon 1 multiplied by electric field 1 normal minus epsilon 2 electric field 2 normal equals to rho s equals to rho s.
Rho. Yeah.
Yep.
Rho s is equal to 0.
Rho s is 0.
0.
Perfect.
Epsilon 1 multiply
Normal component of electric field intensity 2 is equal
field
to
epsilon 1 multiply electric field 1 normal divided epsilon 2.
okay. And normal component of electric field intensity 1 is first of all
1 z minus z3 cosinus 370.
okay. Let me write here electric field intensity. Well, normal component of electric field intensity in the first material is minus
z
multiplied by 3
cosine 3 cosinus 377.
like this.
Yeah.
What about k?
Okay, constant.
Yeah.
K,
It should be somewhere here.
yeah, K constant.
You forgot about K. Don't forget. Z multiplied by K multiplied by 3 multiplied by cosine 377 T. Okay, perfect.
Yeah.
Now, epsilon 1 is given, epsilon 2 is also given. Epsilon 1 over epsilon
Yeah.
2 is equal to 4.
For
Okay.
12.
Multiplied by minus Z multiplied
3.
by K multiplied by 3 multiplied by cosine. Okay, let me decrease the scale. So K multiplied by 3 multiplied by cosine 377 T and is equal
Yeah.
to
Minus Z K 12 cosinus
12 cosine 377 T. Perfect. What about what about tangential component? What about tangential component?
tangential component electric field 1T is equal electric field 2 tangents. Mana, the first form.
Okay, and
Yeah.
it is
We put.
easy.
Yeah.
Okay, tangential component of electric field intensity 2 is equal to the tangential component of the first and is equal to K x plus
K
y multiplied by 2
plus Y 2
cosine
cosinus.
377 T. Perfect.
Yeah.
Okay.
Electric field 2 is equal electric field 1 normal plus 2.
E2
Electric field
normal plus E2 tangential and E2 is equal to K
x K
x plus y multiplied by 2
2
minus 12 z
Z
by 12
multiply 12 and cosinus 377 T.
perfect.
Yeah. D is equal epsilon 0 multiply electric field. Yeah. Simply. We found this.
Okay. Now let's move to the next problem. Okay. Sorry. The next problem is more or less the same, but it deals with both magnetic field and electric field. Okay, and the picture of our problem is this. So let's read the problem. An interface between two general materials contains both a current density given as Js and a uniform surface charge density given as rho s equal to 10 to minus 9. The static magnetic field intensity and static electric field intensity in material are, well, please pay attention here. The magnetic field intensity is static, and also the electric field intensity is also static. It means they don't depend on time, and H1 is equal to this, and E1 is equal to this. Okay. Material properties are given in the figure. Here mu1 is equal to 2 mu 0, E1, epsilon 1 is equal 4 epsilon 0, and epsilon 2 mu 2, and rho s and js is given. Okay, we need to calculate electric field intensity in material 2 and magnetic flux density in material 2. Please note that static electric and magnetic fields are independent of each other. They don't depend on each other. So let's start from the electric field. Tangential component of electric field in the first material is x multiplied by 100 plus y multiplied by 20, and a normal component is minus z multiplied by 100. Now, from the previous problem, we know that tangential components of electric fields are equal. Okay, and for the normal components, we have a relationship which is tangential components are equal. For the normal components, let me open a new page. For normal components, we have relationship epsilon 1 E1 normal minus epsilon 2 E2 normal equals to rho s. Now, in our case, rho s is not 0, so we need to deal with rho s also. And normal component of electric field in the second material will be equal to epsilon 1 E1 n minus rho s over epsilon 2. Okay. Now, it is equal to epsilon 1 was equal to 4 epsilon 0. 4 epsilon 0 multiplied normal component of electric field 1 is minus 100. Multiplied by minus 100 minus rho s was given as 10 to minus 9. over epsilon 2 is given as 2 epsilon 0. Now let's compute the numeric values. Minus 400 multiplied by epsilon 0 is 8.854 10 to minus 12 minus 10 to minus 9 over 2 multiplied 8.854 10 to minus 12. And if we compute the numeric value for this expression, it will be equal to minus it will be minus 200, so 256.47, and it means that normal component of the electric field in the second material is equal to minus Z multiplied 256.47, and from this okay. And now we know the tangential component and we know the normal component of electric field intensities. Now we can write electric field intensity in the second material. E2 equals to, so tangential components were x multiplied by 100 plus y multiplied by 20. X multiplied by 100 plus y multiplied by 20 minus, and normal component is minus z multiplied by 256.47, and unit of measurement is volt per meter. Okay, now let's switch to magnetic field intensity. Okay, H1. So again, let's write the tangential components of H1. Tangential component of H1 is x multiplied 10 to the power of 5 plus y multiplied 10 to the power of 5. And normal component of H1 is minus z multiplied 10 to the power of 5. Okay, now let's okay, we are asked, so I made a bit confusion. We are asked magnetic flux density in material 2. Magnetic flux density is B. We are asked to find B. So in that case, first of all, let's define B1. B1 is equal to mu1 h1, and similarly the tangential component of b1 is equal to, so mu1 multiplied h1 t, which is x multiplied 10 to the power of 5 plus y multiplied 10 to the power of 5, and a normal component of b1 is again mu1 multiplied by minus z 10 to the power of 5. Okay, we need to find b2. So how can we proceed? We need to find b2. How can we proceed? We have general boundary conditions, normal component multiplied by, so b1 over mu1 minus b2 over mu2 equals to the Js, surface current density Js, from this with some manipulations we can find n cross b2 will be equal to n cross b1 over mu1 and normal cross b1 over mu1 minus Js, and everything multiplied by mu2. Okay, and from the definition of cross product, we know that this is equal to the tangential component of the magnetic flux density in the second material. Okay, and okay, if we look to our picture, to the minus tangential component probably.
Bu statik emasmidi? Vaqtdan zavисит qilmaydigan.
Sorry?
Statik emasmidi bular deyman. Anaqa vaqtdan zavисит qilmaydi deysiz.
Yes. 2 here stands for tangential component, not for time. Okay. Okay, and we can write that b2 tangential equals 2. So here instead of n we put minus z. Cross b1 over mu1 minus js multiplied by mu s. Okay, now we can sorry, here z is plus, not minus, should be, or no. Wait. Okay, one moment. Probably I did a mistake. Okay. Here I wrote that n multiplied b2 is b2t, but it should be minus tangential of b2. Yes, now it makes sense. Minus b2t equals, okay, instead of n we put minus z. Okay, minus z cross b1 over mu1 minus js by mu2, and so let me copy this to a new page. And now if we multiply by minus 1, we get tangential component of b2 will be equal to, here minus will be plus z cross b1 over mu1 plus js multiplied mu2. Now let's put the numeric values for b1 and js. Equals to z cross b1 was given as so b1 was given as x let's look at b1. b1 is mu multiplied by h1, so mu1 h1 is x by x by 10 to the 5 plus y multiplied 10 to the 5 minus z multiplied 10 to the 5 multiplied by mu1 over mu1 plus js was given as x multiplied 10 to the power 5 multiplied by mu2 was given as mu0 multiplied by mu0. Compute the final value. We have for tangential component of B2 will be equal. So mu1 and mu1 simplifies. So z cross x gives us y. Z cross y gives us minus x. And z cross z gives us 0. So what we have? Y multiplied 10 to the 5 minus x multiplied 10 to the 5 plus x multiplied 10 to 5. Minus x and plus x simplifies and remains only y multiplied 10 to the power of 5 multiplied by mu0. We found the tangential component of the B2 and normal component according to our boundary conditions. Normal component of magnetic flux density is continuous. That's why normal components are equal at the boundary, and B2n equals to, so normal component was equal to, it was written here, no, it was written here. Normal component mu1 multiplied by minus z 10 to 5. So mu1 is 2 multiplied by mu0 multiplied by minus z multiplied by 10 to the power of 5, and normal component of the B2 is minus z multiplied to mu0 multiplied 10 to 5, and magnetic flux density B2 will be equal to y multiplied 10 to 5 plus or minus, not plus, it should be minus z multiplied by 2 by 10 to 5 multiplied by everything multiplied by mu0. Okay, this is the magnetic flux density in the second material. Okay, have a rest of 10 minutes. After we will continue.